Hello everyone, I am Dr. Fawzul Atiq. I'm giving some series of lectures on the course Probability and Statistics. So in the previous lecture, we have talked about the multiplication rule, which is related to the conditional probability. We solved a couple of examples. So in today's class, we'll start with a independent event. What is that? Two events A and B are said to be independent if the occurrence of one event does not affect the probability of the occurrence of the other. What does it mean? So I have two events A and B. Now these two events are such that suppose B events have already occurred or not, it does not matter. For the this event B, whether it occurred or not, it does not matter to the event A. Right? Because A is completely independent of B. Similarly, the A event has occurred or not, that does not depend for B. So B will have independent probability, A will have independent probability, right? So in this case, we'll talk that these two events are independent. Now you see that if you have such type of independent event A and B, now you think about the conditional probability of A given B. What does it mean? It is the probability of the event A when B has already occurred. But you note that A and B are independent. So the event A does not care about the event B. Therefore, probability of A given B is equal to probability of A. Because whether the event B has occurred or not, it does not depends. So it is equal to P of A. And in the same way, we can also say that P of B given A is equal to P of B. Right? Now we know the multiplication rule of probability that we have discussed in the previous lecture, which says that P of A intersection B equal to the one form maybe I am writing P of A into P of B given A. Now if the events A and B are independent, then P of B given A is P of B. So it is equal to P of A into P of B. So then what we got finally, if two events are A and B are independent, then probability of their intersection is equal to probability of A into probability of B. Correct? So this gives you the definition of independent event. The two event A and B are independent if P of A intersection B equal to P of A into P of B. And otherwise, if this relationship is not happening, then you can call that A and B are dependent. Let us solve few examples. We'll understand these things. Look at this problem. A card is selected at random from an ordinary deck of 52 playing cards. If A is the event that the selected card is an ace and H is the event that it is a heart, is this event A and H are independent? Let us see, because we know the definition of independent event. Let us find out this thing. Now it is given that A is the event that selected card is an ace. Then what should be the probability of A? So how many total ace is there in standard deck of 50 cards? There are 4. So it is 4. Number of favorable cases for the event A is 4 divided by total number of cases, which is 52. It is 1 by 13. Right? And in the same way, we can say that what is the probability of H? That means probability of the event that you get a card which is a heart. How many heart are there? There are 13. So number of favorable cases of H is 13 divided by total number of cases, which is 52. So this is 1 by 4. Now what is the event A intersection H? That means what is the probability of the event that you got an ace which is a heart. So how many such cards are there? You have only one ace of heart is there. No? So probability of A intersection H is equal to 1 by 52. Now this one I can also write it. Now what is P of A into P of B? P of A into P of H. It is 1 by 13 into 1 by 4, which is basically 1 by 52, which is same as P of A intersection H. So what you got? You got P of A intersection H equal to P of A into P of H. What does it mean? That the events A and H are independent. The events A and H are independent. Clear? Okay. Let me show you the proof. This is we have done already. This is a very easy one. Now we have a result on independent event which says that if E and F are independent, then E and F complement are also independent. Correct? So you have if E and F are independent, then E and F complement are also independent. How to prove it? This one we can easily prove it. So what are the things are given? E and F are independent. What does it mean? From the definition we can say that P of E intersection F is equal to P of E into P of F. This is given. What you have to prove? Required to prove P of E intersection F complement, that should be equal to P of E into P of F complement. This is required to prove P of E into P of F complement. Now we will try to prove that. So I'll just remove this part and I'll work on this part. Now E intersection F complement is what? It is, suppose this is the sample space. We have E here, we have F here. The E intersection F complement, this is E event, this is the event F, this is the sample space. E intersection F is this part, the red color one. This part is the E intersection F. What is this value? This is, so this is basically P of E minus P of this intersection part, P of E minus P of this intersection part. So therefore P of E minus P of E intersection F. So we have these things. Now P of E intersection F equal to P of E into P of F. So therefore I can have P of E intersection F complement equal to P of E minus, because this value we will put it this one, it is P of E into P of F. Take P of E common, we get 1 minus P of F. But 1 minus P of F is what? It is P of F complement. So what we got? We got P of E intersection F equal E intersection F complement equal to P of E into P of F complement. And it means that E and F complement are also independent, provided E and F are independent. Very easy result. Okay. Next, I'll move to another result. This one we have already discussed. Then this one, okay. This is the whole proof. You can see that we have just now proved. Now we have an example. A coin is tossed 3 times and the 8 possible outcomes, we all know that like so all 3 are happening head, head, head. Next is first 2 are head, second one, third one is tail. Like that we have 8 number of events, 2 to the power 3, which is 8 number of total outcomes, which is the sample space, and they are assumed to be equally likely. If A is the event that a head occurs on each of the first 2 tosses, B is the event that a tail occurs on the third toss, and C is the event that exactly 2 tails occur in the 3 tosses. Now you have to show that the events A and B are independent, whereas B and C are not independent. So how can you do that? So what are the event A? The outcomes of A? A is the event that it is showing telling that a head occurs on each of the first two tosses. So what are the outcomes of A? It is H, H, H. First two tosses are head. The next is H, H and T. Do you have any other? We do not have. So it is this set. What is the event B? B is the event that a tail occur on the third toss. So only in the third toss you should have a tail. What are the outcomes for B? It is H, H, T. Where tails occurs in the third one. Then H, T, 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 H, T and T, T, T. All these places tails occur in the third toss. And what is the event C? It is the event that exactly two tails occur in the three tosses. So exactly two tails. So what is the event C then? It is HTT, then THT and TTH, where exactly two tails occur. Right? Now let us see what is the probability of A, B and A intersection B, all this. Now let us also see that what is A intersection B. Sorry, A intersection B. What is this event? So it is HHT, only one. And what is B intersection C also? Because I need this. B intersection C is this is HTT, then THT, this two only. Now let us see their probability. P of A is what? We have two elements, so 2 by 8 is equal to 1 by 4. What is P of B? P of B is equal to 4 by 8, whole number of elements in B divided by total number of outcomes, which is 1 by 2. Then P of A intersection B, it has only one outcome, so 1 by 8. So therefore, we can see that P of A intersection B is equal to PA into P of B. And therefore, the events A and B are independent. Therefore, the events A and B are independent. Next, what is P of C? P of C is equal to 3 by 8 because it has three number of outcomes. And what is P of B intersection C? It has 2. So 2 by 8 is equal to 1 by 4. And therefore, I can easily see that P of B intersection C is not equal to P of B into P of C, because P of B is 1 by 2, P of C is 3 by 8, which is not equal to 1 by 4. Therefore, the events B and C are not independent, and therefore B and C are dependent. Clear? So I am going little first in this examples because these are very easy kind of examples. So this is the whole proof that we have discussed. Just now we discussed. Okay, next one. Now it is given that E is independent of F and E. Right? E is independent of F and E is also independent of G. So is it necessary that E is independent of F intersection G? So there will be a natural question that E is independent of F, E is independent of G. So will E be always independent of F intersection G? Let us see. The answer is no. Right? So how can we say? Let us see some example. Two fair dice are thrown. Let E denote the event that the sum of the dice is 7. F denote the event that the first die equals to 4. G denotes the event that second die equal to 3. Then what is the probability that what is the probability of P of E, P of F and P of G? Then what are the probabilities of P of E intersection F? All of their individual probability, along with that the all three intersections probability. And finally you have to see that R, E and F are independent, R, E and G are independent, and E is independent of F intersection G. We'll see, let's see. So the event E, so you were throwing, sorry, just a second. So you were throwing if two fair dice. So how many total number of outcome you have? You have for one dice it is 6. For another dice also it is 6. So 6 into 6, there are 36 number of outcomes will be there by basic principle of counting. We have already discussed in the first few classes. Now E is the event that the sum of the dice is 7. So what are the outcomes in E where sum of the dice is 7? First die is 1, second is 6, then 2, 5, then 3, 4, then 4, 3, then 5, 2, then 6, 1. These are the event where the both the dice sum the face whatever value you get. If you add them, you will get this sum is 7. How many such cases are there? There are 6 cases. What are the event outcomes of the event F? It is the event that the first die equals to 4. So it is the outcomes are 4, 1, 4, 2, 4, 3. These are the outcomes for the event F. 4, 4. Because the first one should be 4 and the second one can be anything, any of the 6. So these are the outcomes of the event F. Again, it has 6. And the third one is G is the event as the second die equal to 3. So the first one may be 1, second die should be 3. Then this is 2, 3. So these are the outcomes of the event G. So we are writing the outcome of the event G. 4, 3, sorry. It is 4, 3, 4, 4. Sorry. Is 5, 3 and it is 6, 3. Right? So all of them have 666 element. Now you also see that what is E intersection F? E intersection F has, is there any common element in them? Yes, it is 4, 3, only one. Then E intersection G is what? Is there any common outcome? E intersection G, it is 4, 3. This is the event outcome. And F intersection G is what? F intersection G. So it is also again only one, which is 4, 3. Right? And what is E intersection F intersection G? So E intersection F intersection G. So it has 4, 4, 3. So this is again 4, 3. This outcome. So all of them have 1, 1 outcome. Now you can easily see that what is the probability of E, F, all these things immediately you can get. So as you see that probability of E is equal to, maybe I'll show you the directly the answer. The probability of A is, sorry. Yeah, the probability of the event A, E, F, G, all of them are 1 by 3, 1 by 6, 1 by 6, 1 by 6. And E intersection it is 1 by 3, 36. This is 1 by 36. All of them are 1 by 36, like that. And therefore, we can see that P of E intersection F equal to P of E into P of F. P of F into E intersection G is P of E into P of G. So they are independent, right? E and F are independent. E, F, G are independent. But E is not independent of F intersection G. Why? Because P of E, this value is equal to 1 by 6, whereas this value is equal to 1 by 6 into 1 by 6. So they are not equal. So therefore, E is not independent of F intersection G. Clear? It's an easy problem. Okay. Now, yeah, we'll have a few more notes. The outcome to unrelated parts of an experiment can be treated as independent. Suppose we have one experiment where two parts you have or few number of parts you have which are not related to each other, right? Then also we can treat them as independent event. Like, look at this example. What is the probability of getting two heads in two flip of a balanced coin? So what you are doing, you are flipping a coin, you should get a head. Next, again, you are flipping a coin, you should get a head. So does it depend? They are the unrelated thing, na? So first one is getting head, and second one again you are throwing. Does it have any, like the to probability of getting head? Does it have any effect? The previous one you got head or tail? No, right? So they are independent. So what is the probability of getting two heads in two flip of a balanced coin? So it should be the probability of getting a head in the first one into probability of getting head in the second one, right? So we can immediately write the solution for this uh, question as, yeah, so probability of getting two heads equal to 1 by 2 into 1 by 2 equal to 1 by 4. Because they are not physically connected, so we can treat them as independent. I hope it is clear. So probability of getting head in the first one, it is 1 by 2. Into, because they are independent, probability of getting head in the second one, it is 1 by 2. Therefore, it is 1 by 2. Now look at this example. Two cards are drawn at random from an ordinary deck of 52 playing cards. What is the probability of getting two aces if the first card is replaced before the second card is drawn? That means you have a standard deck of 52 cards. You are taking one. You have to find the probability of getting it ace or not. What is the probability of getting it ace? And then you keep it again in the same deck. So you'll have again 52 number of cards, and in the second option again you are finding the probability of getting an ace. So these two events are independent, they are unrelated part of the experiment, right? So therefore what we can do, just we can solve the problem. Since there are four aces among 52 cards, so probability of two aces with replacement, it is 4 by 52. In the first selection, you will have, what is the probability of getting an ace out of 52 cards? It is 4 by 52 into, again, what is the probability of getting one ace out of 52 cards? Because you have four number of aces, so 4 by 52. So this should be the probability. Now the second question says the first card is not replaced before the second card is drawn. Now there is a gap. So your first event is a 4 by 52, right? That probability of getting an ace. Now once you get that ace, you are not keeping it in the standard deck. So your standard deck of 52 card become 51 number of cards. And how many aces are remaining? There are three number of aces are remaining, right? So in this case, you will have the probability of two aces without replacement. It is 4 by 52 into 3 by 51. So is equal to 1 by 2 to 1. Therefore, we observe that the independence is violated when the sampling is without replacement. I hope it is clear. Okay, let me move to the few new concepts. Now we have seen that independent event definition, that whenever you have two event, then they are independent, means their intersection probability should be equal to their individual probabilities product. So if there three are independent, then you have to have this product is equal to all three intersections should be equal to their multiplication. Then individually, if you take uh, of the event, all the two combination, they should be also their individual probabilities product. So this is the definition of probability of three events. Now if you have n number of events, we can certainly extend this. So we should have their all of their whole intersection is equal to their individual probability sum. Then you extend this result. Then you take the 3 among them, that should be also intersection of their 3 probabilities product. Then 2, like all possible combination from 2 to n. So we'll have that P of EI1 intersection EI2 intersection EI are equal to their individual probability, where 2 is less or equal to or less or equal to. Like you have to take two possibilities, two combinations, their product is like this. You should have two combinations, all three combinations, next all four combinations, like next the last one, which is the all n combinations. So all should be their individual product. Then you count them that E1, E2, En are independent event. Right? Now we'll have a very interesting example, which is very good one. Let us understand that. A system composed of n separate components. It is said to be a parallel system if it is parallel system if it function and when at least one of the component function. Right? For such a system, if component I independent of other components functions with probability pi, then what is the probability that the system function? Right? A system composed of n separate components. It has n number of components. And it is said to be a parallel system if it functions when at least one of the component functions. So at least one of them, if it function, then you said it is a parallel system, and that means the system will function. Now given that for this system, if component I, which is independent of other component, and it is function with probability pi, so the system 1 will function with probability p1, system 2 will function with probability p2, like that system n will have is functioning with probability pn, small p1 p2 pn. Now the question is, what is the probability that the system function, the overall the system function, right? So let us assume that let ai denote the event that the component I functions. AI is one particular event, which is the component I. What do you mean by A1 then? A1 is the event that the first component is functional. A2 is the event that the second component is functional. Like that, you have n number of event. Now, what is the event that the system functions? That means whenever at least one of this A1, A2, and dot up to AN, at least one of them are functioning. That is by the definition the system functions. Now at least one of that means at least one of the event happened. So what you have to find? We have to find the probability of this event. Sorry, it's not union, it's not intersection, but it's at least we have to do, right? So it is A1 union A2 union A union AN. We have to find the probability of this event. It means that at least one of the event A1 A2 AN happens, and which basically says that their union. So we have to find the probability of this. Now, we can write this one in a, because all the events A1, A2, N are independent, right? So I just wanted to do this one equal to, can't I write that A1 complement intersection, A2 complement intersection, intersection AN complement, and then whole complement? How can I write this? By De Morgan's law of sets, which are the events. So therefore, I can write this one. And then we know that it is the probability of a complement of event is 1 minus probability of the event A1 complement intersection A2 complement intersection intersection AN complement. Now A1, A2, AN all are independent, so their complements are also independent. So I can certainly write that 1 minus P of A1 complement into P of A2 complement P of AN complement. Now what is the probability of A1 complement? Probability of A1 is small p1, right? Probability of P of AI is equal to small pi. It is given. Here it is given for I equal to 1 to n. Therefore, P of A1 complement is 1 minus P1. Similarly, P of A2 complement is 1 minus P2 dot 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 1 minus Pn. This should be the answer, right? This is the probability that the system functions. I hope you understand. Okay, let me move to the, this one, as we discussed, we can also write the answer in this way. That P of the system function, it is 1 minus the system does not function. The opposite of the event. So system does not function means what? All components do not function. That is the definition, that when you can say that system function, when all of them are not functional. And all components do not function means it is the intersections of the event, A1 complement, A2 complement, and AN complement. And because they are independent, you can write down in product form and you can write the answer in this way. Okay? Okay. Let me move to the next example. Now, these are very easy example. Find the probability of getting 3 heads in 3 independent tosses of a balanced coin. How we can do that? The first one, so you have to do consecutively. So first probability of getting 1 head, it is 1 by 2. In the second one, again to get it, the another head, it is 1 by 2. Third case, again it is 1 by 2 because all of them are independent. So then we can easily say the answer is 3 heads, it is P of head into P of head into P of head is equal to 1 by 2 whole cube. We have one more example. Find the probability of first rolling 4 fives and then another number in 5 rolls of a fair die, right? So you basically you have 5 rolls. You are going to roll it that 5 times. So you are going to roll a dice 5 times. You have to get the first 4 are 5, right? So here you should appear this is 5, then this is 5, this is 5, and this is 5. And there you have to get it is in another number. So it should be that maybe I can say 5 complement. That means other than 5. Now whenever you are throwing a die, whatever is the probability to get it, it is a 5 face, the face 5. In the next time again, what if you do, they are independent of each other, right? So what is the required probability, this desired probability? So what is the probability of this event? It is 1 by 6. Next is again 1 by 6. Next is again 1 by 6. Next is again 1 by 6. Then the last time it says that it should be other than 5. So how many outcomes are there like that which are other than 5? There are 5 number of outcomes. Total number of outcomes is 6. So this is the probability. So the required desired probability is 1 by 6 whole to the power 4 into 5 by 6. Because all of them are independent event. Clear? I hope you enjoyed these lectures. So this is the one as we discussed. The whole solution is given here. You may have just a snap of it. So I hope you enjoyed all the contents we have taken from this. Mostly we have taken from these 2 books and few more books also I have used. So if you really enjoyed the class, give your feedback. If you like it, that you just share your feedback. Thank you very much. We'll meet in the next lecture.